told that the production manager knows that 5 personal components produced by a particular manufacturing process have some defect. 6 of these components whose characteristics can be assumed to be independent of each other are examined, and you want to find probabilities related to this. So the first thing to recognize here is that first thing is that we should always define a random variable. So what we're interested in is the components. Like if you notice in all of these parts, what we're interested in is components have defect, right? This is what we are interested in, right? So the first step is going to be to define a random variable in terms of whatever we are interested in finding, right? So let the random variable x denote the number of components that have a defect. Right, so over here, again, what we're interested in is this, right? In each of the part, you can see we're interested in finding that either none of the components has a defect, one of the components has a defect, two of the components have a defect. So what we're interested in is the number of components that, just a second, the number, okay, so this is not, this is supposed to be the, okay. So we're interested in the number of components that have a defect. So we're defining a random variable in terms of that, right? So x is essentially, here if you notice, now the next thing to notice is x is a binomial random variable where n is 6 and p is 0.05. Over here, again, the key is to understand that success is defined as, so note success here is defined as success here is defined as component has defect. Right, this is how we've defined success, right? Interested number of components that have a defect. Let's just erase this for a minute and let's see if we can. Yeah, okay, so I wanted to make this component has a defect, right? Okay. So over here, our interest in success is the component has a defect, and you can see from here that this is a binomial random variable. Again, binomial random variable, why can we apply binomial? Because we have a finite number of components, 6, right? So we have a finite number of components, and then we're assuming that the properties of the components are independent of each other. Because remember, you need a finite number of independent trials. So over here, that translates into a finite number of components whose properties are independent of each other. And we have a constant probability of success, 5% given to us. Remember, success is in terms of whatever we're looking for. Here we've defined it in terms of the component has a defect, right? So, and also it's always important to keep in mind what values does a random variable take. So we know binomial random variable takes values from 0 to 1, right? 0, 1, 2, because obviously the number of successes that you can have range from 0 to the total number of trials that you do. So, you know, in this case, like for example, it could be that none of the components have a defect, or all of the components have a defect, or some middle value in between. So always, so this is important, okay, always note what values does random variable take on, right? This is important and we'll look in a bit why. So we define all of this. Let's just clear this up a bit and then let's just write one thing here. So we've cleared this up. So we have this uh binomial, right? Random variable. Let me just quickly write this much only. Okay, x is binomial, n is 6, p is 0.05. Where x takes value 0, 1, 2, and in a bit we'll see in part C particularly why it's important to keep note of the values it takes. Let's do part A. Part A is the probability we want to find that none of the components has a defect, because we define x to be the number of components that has a defect, so the probability x is 0. We want to find that. For this, let's first recall what the PMF of a binomial random variable is. Recall PMF of binomial random variable x. So in general, the PMF is probability x is k is equal to n choose k, pk, 1 minus p, n minus k. Now in this particular case, you know, n is 6, and k is sorry, in this case n is 6 and p is 0.05, like we saw from here. So probability x, so we can write its formula for like PMF as 6 choose k, 0.05 power k, and then 0.956 power minus k. Now we'll just use this, right? Now probability x is 0. Now probability x is equal to 0 means you want to put k is equal to 0, right? So it's going to be 6 to 0, 0.05 power 0, 0.95 power 6 minus 0, right? And when you do this just turns out to be 0.735. So this is the probability x is 0. Now the next part they ask us to find the probability that x is 1. Let's just do it over here. So now we want to find the probability x is 1. So now we'll just put k is equal to 1 here. So this will be 6 choose 1, 0.05 power 1, 0.95 power 6 minus 1. And this will turn out to be 0.232. Now I want to find the probability that at least means greater than equal to. So we want to find the probability. Now here it will be important. We'll see why we need to know what values does a random variable take on. Probability x is at least 2. Right? Because remember, what does at least mean? At least means greater than equal to, right? So what you're gonna do over here, sorry, is basically, so probability x is at least 2. What I'm gonna do is I'm gonna apply the complement rule here. We'll see in a bit why. We'll later discuss the alternative way to do this. Okay, so one way to do it is so one way you could do it is probability x is at least 2. Again, here, again, it's important to keep in mind values it takes because at least 2 means 2 or anything greater than 2. But we know it only takes values till 6. So this means we'll go from 2 to 6, right? So this is why it's important to keep in mind what values does it take because say we're saying over here we're starting at 2, but we need to know where we're ending. And for this, we need to keep in mind the values it takes. Probability x is at least 2 means probability x is 2 or x is 3. This is one way to do it. Or x is 4 or x is 5 or x is 6. This is one way we could have done it using this. But this is a relatively longer approach. It's a lot better to use the complement rule and we'll see in a bit why now. So if I apply the complement rule over here, right, so probability x is greater than equal to 2 would be 1 minus probability x is less than 2. Because remember the complement rule is, what is a complement rule? We know the complement rule is, so the complement rule is that probability of A is 1 minus probability of not A. Right, so the probability x is greater than equal to 2 is 1 minus probability x is not greater than equal to 2, which basically means that probability x is less than 2, right? Now, often when you see at least, so often when you see at least, it requires use of complement rule. It's easier to use the complement rule here. It requires use of complement rule, right? Because now you see the complement rule requires finding less probabilities than if I had done it directly like this. So over here, what we're going to do now is going to be, let's see what probability x is less than 2 is, right? So typically when you see at least, it does require to use the complement rule. Probability of A is 1 minus probability not of A. And the not of the complement of x greater than equal to 2, like the opposite of this is x is less than 2, right? So 1 minus, now probability x is less than 2. Again, we know x has to be less than 2, but what values do we take? For this, we need to keep in mind what values can the random variable take, right? And you know that's 0 or 1, right? So this is why it's always important to keep note of the values the random variable takes so that we can identify them. So x is less than 2 means that the probability x is 0 or x is 1, right? That's what it means. Right, so probability x is less than 2 means x is 0 or x is 1, right? So now what we're gonna see over here is basically going to be, okay, probability x is 0 or x is 1, right? We know okay, when we're finding probabilities for a discrete random variable, what we typically do is, like if you want to find using the PMF probability of a discrete random variable, we just sum up the PMF over those values of the discrete random variable. Like what I would do have done in this case is to find the probability x is less than 2 because I know x could either take a value 0 or it could take a value 1. So we'd just sum the probability x is 0 plus the probability x is 1. But let's try to understand why the summing works, the logic behind it. The logic behind this is, like we talked about, okay, we want to find the probability x is 0 or probability x is less than 2 is probability x is 0 or x is 1 because it can only take values, x can only take values 0 to 6. So again, firstly, keep in mind what values can it take to identify what values do you have, right? Or means union, right? So I can write this as 1 minus probability x is 0 union x is 1. And you can write it like this. Now, we know that probability of union of mutually exclusive events is the sum of their probabilities. Now, a random variable taking on different individual values are mutually exclusive events because when you perform a random experiment, you get exactly one outcome. So you're only going to get one value of the random variable corresponding to that outcome. So random variable taking on different individual values like x is 0 or x is 1 are mutually exclusive events, right? And because they're mutually exclusive events and the probability of union mutually exclusive events is the sum of the individual probabilities, that is why this works, right? So the since mutually exclusive, right? So it's important to keep in mind why when we say okay, if you want to find the probability x is less than 2, typically we know okay, when we have to find the probabilities of a discrete random variable from its PMF, which is the sum of the PMF for those values of discrete random variable, right? Probability x is less than 2 would be probability x is 0 plus probability x is 1. But how do you get from here to here? What is the logic behind it? From here to here, the logic behind this is the probability x is less than 2 is probability x is 0 or x is 1. And or means union. And because the random variable taking on different individual values are mutually exclusive events, the probability of the union is the sum of the individual probabilities. So that is why probability x is less than 2 is essentially the probability x is 0 plus probability x is 1. So now we already found probability x is equal to 0 in the first part as 0.735. And the probability x is 1 is 0.232. And from here, then we could find the probability x is greater than equal to 2 by just adding these up and then subtracting from 1. Right, so obviously this is a lot easier than doing this because if we use the complement rule, then we're essentially just using part A and B's answers and we don't have to compute multiple different probabilities. But obviously, if we hadn't used the complement rule, then we would have to find 1, 2, 3, 4, 5 probabilities, right? So that's a lot more tedious and longer than just simply recognizing that here complement rule is easier to use. So whenever you're finding a probabilities for discrete random variable, like in this case binomial using its PMF, first things first, keep in mind the values that it can take. Because for me to identify probability x is greater than equal to 2 means x could be 2, 3, 4, 5, 6. I need to know what possible values it can take. Similarly, to be able to identify the probability x is less than 2 means x can be 0 or 1. Again, we need to identify what possible values it can take. So first of all, you should always keep in mind the values it can take. Secondly, we should always check if it's easier to use the complement rule. Typically, when we say at least or at most, it does make it easier to use the complement rule. And then lastly, the logic, we understand now that why when we want to find the probability of a discrete random variable using its PMF, why can we sum up the PMF for those values? We've seen the logic because OR means union and random variable taking on different individual values are mutually exclusive events and probability of union of mutually exclusive events is the sum of the individual probabilities, which is why when we write probability x is less than 2, we can write it as probability x is 0 plus probability x is 1.